Hello everybody, and welcome to another session of project shows of the Swiss Space Center IGLUNA field campaign. I am Jesus Manuel Muñoz Tejeda. I'm a space technology advisor and systems engineer from the IGLUNA project. And today I have with me a German team from Aachen University called AMPEX, which is bringing us a new game-changing technology for the space and moon exploration. Basically, they're using the lunar surface as a primitive material in order to develop devices, electronics, and everything we can imagine from Earth. I have been in the talk with AMPEX before, and I think they are ready to put forward a very awesome project. For everybody that is looking this online, we have a survey in the description. If you could fill us, it will be very beneficial for the Swiss space community in order to know who is watching these kind of videos. And now I will leave you with AMPEX, and I will see you at the very end with the Q&A session. AMPEX, the floor is yours.
Hello, everyone. My name is Juan Carlos Araño Romero. I'm the team leader of AMPEX 20, the project which I will be proudly presenting to you today. I will first speak shortly about the team working on the project, their motivation and its mission. Then I will introduce you to the system and its subsystems. Afterwards, my teammates will present the part of the project they have been responsible for. Without further ado, let's start this presentation. Our team is mostly composed of engineers from all over the world, specializing in different fields. We have many mechanical engineers specializing in aerospace, development, and design. Furthermore, our team also consists of electrical and environmental engineers. The transport of payload into space, for example, for research missions or the construction and supply of manned lunar stations, pose immense economic challenges, in addition to technologically complex tasks, with costs for payload transport of 1.1 million euros per kilogram to the lunar surface and space projects requiring large freight volumes, weight reduction seems to be essential. However, raw materials from the moon or Mars in the form of regolith are suitable for producing habitat building materials and thus reducing freight costs for further missions into space. For this purpose, continuous mineral fibers, that is, basalt fibers, can be utilized in situ to produce fiber composites, as well as thermal insulation, filters, and hydroponic mineral wool for plant cultivation, among other things. However, this requires a spinning unit that can be operated under space conditions. With the IBOS project, a modular and configurable satellite as payload element, the transport of the spinning unit into space is ensured. Due to the limited space available within the IBOS element, the spinning technology of the system must be miniaturized. The space available inside the IBOS cube for the assembly of our system has an edge the size of 3 CDs in an arrow. We aim to develop a state-of-the-art machine which differs from other analogous technologies by being miniaturized, fully automated, and robust. Now we'd like to show you a video about the Moonfiber project. Without Moonfiber, there will be no AMPEX, as we start from the collaboration with this group of researchers from RWTH Aachen University, who follow the same visions as AMPEX with a much larger scope. Enjoy the video.
For more than 300,000 years, humans have felt an urge to discover the unknown. With perseverance and inventiveness, we have reached the most inhospitable corners of this world. But that was not enough for us, was it? Not long ago, we succeeded in setting foot on our nearest neighbor. The moon has always attracted our attention, full of great mysteries, but also of great hopes. Half a century after that, what keeps humanity from venturing into the unknown once again? Partly, it's just a matter of weight. Sending a liter of bottled water to the moon's surface would cost us $1 million USD. So let's suppose we want to send a lunar base the size of the International Space Station. It would cost us 450 billion USD just in shipping costs. Therefore, the obvious question is, why send it all? Couldn't we just use materials available on the lunar surface? The answer is yes. The lunar surface is composed of regolith, a crust with basalt as its predominant rock type. This basalt is perfect for the production of mineral fibers with a wide range of applications due to its broad spectrum of good properties. For this reason, we, the Moonfiber team at the RWTH Aachen University in Germany, have designed the first fully automated spinning plant for the mineral fiber production under extraterrestrial conditions. On Earth, this technology usually requires 10 meters high and different working levels for operators. Our prototype measures on its largest side only 40 centimeters and automatizes the production of mineral fibers, which has never been attempted before. The eye block is mainly made of carbon fiber reinforced materials and aluminum, which results in a weight under 17 kilograms. Within it, our technology can produce at the very least 180 kilometers of lunar fiber per hour. The modular system of the eye block allows the construction of larger systems simply by assembling them together. Thanks to its standard interface, the interaction between different eye blocks is fully ensured. Moon fibers can be used as thermal and radioactive insulation filters, textiles, composite materials for reinforced concrete, and even mineral wool for growing plants in space. Today we talk about the moon, but who knows what tomorrow may bring? Think of the places you will go.
I hope you enjoyed the video. Now let's continue. The production of glass fiber from heat-strength glass was already known to glass makers in ancient times, and the technology is older than glass blowing. Continuous mineral fibers, for example, glass fibers, are produced by continuously drawing processable raw material melt using the jet drawing process, as shown in the figure function principle. This figure shows the continuous mineral fibers are due to the rapid mechanical tapering of the molten material drops, which emerge from nacelles at the bottom of a heat bushing, that is, a crucible. The most relevant information about the system can be seen in this table. The outer dimension of the cube eye block where the system is mounted do not exceed 40 centimeters on its edge, with a total weight of 26 kilograms. The maximum temperature required for the process is 1,250 degrees Celsius, which will be applied in e-glass as the choice of material for the first test, thus being more reliable. The control of the system is automated locally, but by using a USB cable or Wi-Fi, it's possible to control it remotely. Now, I would like to introduce my teammate, Jungwen, which will talk to you about the high temperature furnace and its thermal analysis.
Hello. So the furnace consists of thermal insulation, induction coil, and crucible. The induction coil will heat up the crucible, and a homogeneous heating of the material in the crucible will take place at 1,250 degrees Celsius. Raw material is molten with special consideration of risk minimization for other components and efficiency in terms of power consumption. The thermal insulation serves several functions, such as improvement of self-efficiency by containing the heat, and sealing of the crucible to prevent foreign objects from entering. Our team performed a numerical analysis and simulation while designing the insulation. Due to the induction coil, the insulation design is rather complex. We had to account for several types of heat transfer. There are three types of heat dissipation: radiative, convective, and conductive. Radiative heat transfer takes place between the crucible and insulation. Convection takes place inside the insulation, and lastly, conduction through the walls of the crucible and insulation. Besides that, There is an active cooling from the induction coil to the insulation walls. It is established that the cavity radiation around the nozzle of the crucible has a substantial effect of the heat distribution in the lower part of the insulation, and the cooling of the coil has a large effect on the required thickness of the radial insulation. Now my teammate Philip, who's in charge of the winding system, will take over.
Hello, I'm Philip and I designed the winding system. The main idea of the manufacturing process of a winding system is that to create one that works as a usual one in the industry, but it's fully automized. So you have to catch a glass drop, pull it into a fiber, accelerate the whole system, wind it around the wheel, and distribute the fiber over itself. These are all tasks that are normally executed by hand by workers on the ground. But because we have to optimize everything, that was the main challenge. So no hand is needed. And of course, other challenges were the weight and the space and the power it takes. And that's why we came up with the hamster wheel design, as we call it. Over several iterations, the winder has evolved a lot, as you can see, from a 3D printed minimal surviving system, which has served as a proof of concept and for first tests. We went over to a first model made from aluminum and steel, to a one that enables easy removal of the fibers, as well as a more linear distribution of them, to the one we wanted to use in the field campaign, which is modularity enable, easy use and data improvements. But unfortunately, some parts didn't arrive on time, so we will stick to an old model that we still have. We also designed a shell for easy and fast removal of the fibers, which can be used later on. Why did we choose this design exactly? Because with low rotational acceleration, the fiber is caught inside of the wheel. It's similar to picking up a spaghetti with a fork. So the more fiber on the reel is, the tighter is the fit. And then we enable a whole fit, which just serves as a perfect catching mechanism. Now, thank you for your attention, and my teammate Reese will take over to tell you something about the automation system.
Hello, everyone. As you can see in the photo, the workers that we're gonna have on our journey into space will be mostly robots. And for our system to work in this in these robot-driven environments, we need a totally autonomous machine that can communicate with us and other systems. For a minimal functioning system, we need to automate three separate sub-processes, and these are the controlling of the temperature, the controlling of the motor movement, and the detection of the fiber status. And for the latter, we used the easiest thermal camera that we could find, and surprisingly, this worked to detect both fiber drop and the fiber break. And other than the controlling system, we also have the task of communicating with the user and inevitably with the other systems. And for this, we made a modular architecture consisting of three separate microprocessor units. And the hardest part of this implementation was the communication module, as we use the notorious serial communication protocol. And in case of a lockdown of the communication system, we installed a watchdog which would reset the communication system electronically if in case there is a lockdown on the microcontroller. And COVID-19 has delayed us to have a complete system, and without a complete system, we couldn't test our automation system extensively as it should be done in a complex system like this. But we proved all of our concepts, and our system is ready to be optimized in a big scale experiment. And now we are going to show you guys a video of our manufacturing process. Sit back and enjoy.
Mining and production in space for space application will be a completely new multi-trillion euro economic sector. This will lead first of all to unexpected possibilities and also to new future-oriented jobs.
Actually, our technology is progressing on a daily basis. And
Just remember when you are done.
Mining and production in space for space application will be a completely new multi-trillion euro economic sector. This will lead first of all to unexpected possibilities and also to new future-oriented jobs.
actually, our technology is progressing on a daily basis. And the key factor of this technology is the implementation of a robust and reliable and sustainable spinning device. Such a robust technology could be scaled up, helping to install habitats and infrastructure on the moon and elsewhere. In addition, as a mobile miniaturized factory, it is supposed to produce fibers on Earth, where resources and space are limited.
Hello everyone, we are now live in front of the spinning machine for fiber production. At the top you can see the platinum rhodium bushing. The material of this is important for the consistency of the process, as well as being stable at the working temperature 1250 degrees Celsius. The molten material reaches the required viscosity to exit through the holes at the bottom of the bushing. As it falls through these holes, it creates jets. At this point they have already fibers which are reached by the winder, which catches them, collects them, and pulls them. After a few seconds, we have enough fibers to be able to work on new components and materials. Now the turn is for those who require a quality product for the construction of extraterrestrial and terrestrial habitats.
Hello again. For the future of AMPEX, we would like to take the system one step further. This is why we believe it is relevant to make the first test in microgravity conditions. The method we have decided on is parabolic flight. That is why we hope to be able to participate in IGLUNA 2021 with the same vision, but with a mission with constraints one step further. Finally, we would like to thank our sponsors for their support and dedication to our cause. Despite the current situation we are all suffering, they stood by us. We are very grateful for the sponsorship of Saxonia with their beautiful platinum rhodium crucible, Maxon's robust motors, and the energy efficient induction system of Cobes. Thanks to Airbus for their support, especially with Blackwave, who manufacture the reliable prototype of our winder. The Distrelec electronics have made it possible for us to automate the system, and the precise pyrometer of Optris has also been essential for this task. Thanks to Aachen for providing us with fire extinguishers for our own safety. Last but not least, we would like to thank to the Hans Hermann Voss Foundation for the financial support, and of course, the unconditional support of our university, RWTH Aachen, and in particular, the Moonfiber team. Thank you very much for your attention and for being here today. Feel free to ask any question and comments that you may have.
Thank you very much, Ampex. Really fantastic. I really enjoyed your project, so the videos were very nice, and it's very good to see that you actually have a working prototype, which is something really challenging during this year because all the situations and difficulties we have had. I have 1,000 of questions about your project. But I don't know that the audience also have some of them. So as you said, let's start these Q&A sessions with some of them. The first one I would like to ask you, Ampex, is because one of the main challenges that we have with moon exploration is bringing all the resources to the moon. And with Ampex, what you are proposing is a system that will use the lunar surface material in order to do additive manufacturing and use the resources in situ. But what happens with the system itself? Do you have to bring everything from Earth? Do you think you can have something set up in the moon already? What do you actually have to bring from the Earth for your prototype to work?
Yes, for the prototype, of course, it's gonna be really lightweight. So we don't really know, we don't really need to bring like the material itself that we are gonna use for the production. So the only thing that we will require for a prototype to work will be the system itself, that it's actually very complicated and really complex. So it's not something that we will be from the beginning be able to produce directly in situ. But once we have enough infrastructures to be able to make more precise, more complex manufacturing directly on the moon, for sure we will be able to produce more spinning units that will be able to produce even a larger infrastructure over the moon.
That's really great, and the actual replicability of your system, I think, is gonna be really challenging, and I think it's something that is very good for your project. because we saw that it was actually modular, that some systems can join together and become a bigger system. So that's really, really good. What happens, for example, for the power system? Because you said that you need to reach more than 1,000 temperature in the furnace. How do you plan to get this high temperature? What power resources do you need for your system to work, and how it will work on the moon?
Yes. So for the reaching this temperature are many approaches. Right now we are working with the most reliable and at the same time energy efficient way to achieve this temperature. That's with induction system, where a current will produce an induced electromagnetic field that will heat the crucible itself and reach this temperature. This process is really, really energy efficient, but there are other approaches like using the sunlight directly to achieve these temperatures on the raw material. So many approaches, but we are now trying to go for the most energy efficient, but at the same time reliable. And this choice is induction system.
That's really good. We saw that you said some possibilities and some alternative. I think that's really, really good. So that brings me to the next question, which is, what is the TRL level of your technology? For everybody at home, the TRL level is a scale from 1 to 9. 1 means that the product hasn't been developed at all, and 9 that is already working. So where is your technology right now?
Yes, that's a very good question. And for that one, my teammate Janina will take the answer. Please, Janina.
Hello, thank you. Currently, the prototype is in stage 3, which would be a proof of concept. Since we already did the development of the prototype, now we're trying to test if it works, and if then we will proceed to the validation, which would be phase 4 and above. Thank you very much.
Great. So I guess you would like to validate the product first on Earth, and then you would like to validate the product then in the moon in the future. Is that correct?
Exactly.
Okay. Excellent. So I have, you know that the Earth and the moon environment is really different from each other. So in case, for example, of the thermal strategies, the partial gravity conditions, and the resources that you can have in the Earth in order to replicate this regolith or the lunar surface in the actual Earth are really different to each other. So how do you tackle these kind of differences between Earth and moon environment?
Yes, well, usually in the development process of a system such so complex as this one, you have to go step by step. So first of all, we are here working on a proof of concept. So what we are trying to see if it's actually possible to miniaturize this whole complex in a small box that has a mounting area of only 35 centimeters times 35 centimeter. That will mean that for the other constraints that we will have under the moon, for example, very strong temperature changes and microgravity. Well, not actually microgravity. We will only have 1/6 of the gravity of the Earth. That will make the process possible to achieve. So it wouldn't be a trouble. But for sure, we will have to take into consideration many constraints, but they are not impossible. I mean, we can do it for sure. And of course, we have to take into account the rocket launch. That's a very technical constraints on there. But nothing is impossible. I mean, we can do it for sure. We just need more time, more money.
I really like your inspiration. Really attractive, really good. As you said, there is nothing impossible, and you have to go step by step. So I guess you would like to test your system, the proof of concept, take your technology readiness level a little bit higher and then test it on the moon and make it bigger and better. And then you could tackle, for example, as you said, the partial gravity conditions, replicate actually with lunar regolith how your system is working. For the lunar regolith, actually, which for the audience at home is basically the lunar surface that is in that over there. Do you plan actually to use, for example, the regolith for Mars or another planets? Because we are talking about moon exploration, but I think your system can be actually set up in another future planets like Mars or even in the moon Titan of Saturn. What do you think about that? Do you think your system can use regolith from another planets? Can it be also used somewhere else?
Yes, for sure. But I would like that my teammate Rhys will answer this question. He knows better about this.
Well, the chemical composition of the planets that we know, as in Moon and the Mars, are treated the same, which we call basalt, and that's why our system will work totally the same with Moon rocks and with Mars rocks, and it's also the same composition of on Earth. So we believe that it will be the same on the unknown planets. So our system will work on almost every extraterrestrial conditions. It needs also to have rocks.
Yeah, that's great. Thank you very much. And can you actually, because I have some questions from the audience asking, what can you actually build with lunar regolith? What are the limitations, the advantages, or the technical difficulties that you may have when you are using lunar regolith as a material for any kind of device?
Yes, that's a very, very good question. For that one, my teammate Philip will answer. Please.
Actually, you can build a lot from moon regolith because we are right now concentrating on the fiber itself, which can be used, as Juan Carlos also explained, for everything, like for reinforcing structures for buildings, or for example, as insulation materials. But the moon rocks themselves can also be 3D printed, for example, with the same principle that we use. So just like melt them up and make additive manufacturing out of them and build homes with everything. Them. So the idea is that a moon village could also consist like mainly of moon rocks.
Great, excellent. What material are you actually using for replicating the lunar regolith? Because I guess you don't have that available right now, right? So what kind of alternative option are you using to test the system?
Excuse me, could you repeat the beginning of the question? I didn't understand.
Sure. I'm asking about the material that you are using for replicating the lunar regolith for your system. Which material are you using?
Okay, so I think that if I understood correctly, you're asking about what kind of simulant material, like regolith simulant, are we using? For the first test, we are working with IGLUNA. IGLUNA is a well-known, really old material that has been since the 50s in industrial production. And there are many informations and data sheets to corroborate. For the first test, you make sure that we are having the right parameters, we are achieving the necessary or the correct, the optimal composition or specifications of this fiber. We will work with IGLUNA. But the second idea is which material will simulate the material on the moon. So this is just a problem of chemistry. We need to have the same chemical composition as the moon rock because we are going to work with the regolith. The regolith, just to explain shortly, it's only the outer area of the crust of the moon. So we have the moon crust, and the outer area, the top is the regolith that is just like dust, kind of dust. So when you have a powder, if you know the chemical composition of that powder and there is only chemical components that exist on the Earth, you can just simulate it. That it's called the moon simulant, and then you can just put it on our machine try to change the parameters and reach produce this fiber. So there are many options. There are many options because the moon has different chemical compositions depending on the landing place or the area that you are researching. So that's part of the scope of the Moon Fiber project. They are working exactly on that scope, but we are only taking care of the miniaturized machine, and this miniaturized machine will be able to be used with any material, as long as you change the parameters to produce the optimal product.
Exactly. I think it's very good that you mentioned that, because having the flexibility in the system to use any kind of material, also joined to the scalability that you can join both of them together, that's really great. I'm thinking, and I saw another question from the audience, that because right now what you are using, I think you are using a manual process in which you put the regolith substitution manually into the system. Is that correct? Yes. Okay. What are the plans in the moon? Do you plan to have a robot to do that for you? How is the automation system? What are your vision or your future vision for your project in the moon? How is it going to work to be fully automated?
Yes, it's a very good question, and that's of course part of the work for the future's teammates on the project. We are trying to keep our scope as limited as possible, because the system itself is already very complex. So if we cannot achieve everything, I mean, it wouldn't be the rightful way to develop a machine. So like the ideas will be that the astronauts itself will be able to fill the interior of the crucible with the materials, but because it will be really difficult that we will have these astronauts 24 hours there for us, we would like to for sure automate this. Our machine, it's capable to allow an automating robot to refill the crucible with more material. That's one of the technical constraints that we input ourselves from the beginning, but for sure it's not part of our scope because it will be too much, but I mean, for sure it's possible. There is,
yeah. And I guess that's within the future plans of the project, because like we said, it's only TRL number 3, which means that the proof of concept is there, and you have a working prototype on the Earth, and then you have to scale it on the moon and test it further. So what are actually the short-term plans of the project? You said that you want to test your product in microgravity flight, that you would like to participate in IGLUNA 2021. How are you going to bring your project to the next step? What is, according to you, what is needed to be done now in order to increase the TRL level of your technology?
Yes, well, as we say before, COVID-19 pandemic has struck really hard in our team, because most of the components that we are supposed to receive, we received them really late, like last week. So we didn't have the time to make sure to do these extensive test procedures to refine the system itself. So first of all, we would like to refine to do these test procedures, and afterwards, when we have already enough data and enough information to be able to keep it with us for the next steps, we will like to continue with the same system, but with different technical constraints, one step further. So this is the idea, to have a parabolic flight, for being able to see the system already working, but under microgravity. Once we can ensure that the system works under microgravity, So if we know that it works with Earth gravity and it works with microgravity, it will work for sure under 1/6 of the Earth gravity, that is the Moon's gravity.
Absolutely. And I think it's really, you have a really clear schedule and timeline on when you want to bring your project. And you actually mentioned that you had some difficulties throughout this year, which I imagine you have had. What do you think, apart from COVID-19, that of course has been a real challenge, it's been the most difficult challenge you have faced during this year?
Yes, that's a very good question. And my teammate, Simon, will take care of it. Please.
Hi. So yeah, since our system is working with high temperature and high voltage, like the major risk is regarded to these. So we came up with several mitigation strategies to ensure the reliability of our system as well as our own health. So besides personal equipment, personal protective equipment, we installed many sensors and thermocouples as well as fuses to make sure we monitor the process as precisely as possible, and yeah, to shut the system down once a critical temperature is reached. We also have developed a checklist to minimize human errors. And yeah, as well as that, we relocated some parts inside our process to yeah, to reduce the risk of interconnectivity. And yeah.
Absolutely. I think that's a very good point. And all these difficulties you have faced throughout the year, I think has been a little bit mitigated by your partners and by the people that has been supporting you throughout this time. And I have a question actually coming from the audience that is asking how the partnership between the automation side of the system and the system itself is going to be. So that brings me to a more larger question, which is, who would you like to be a partner with? Who are you looking for to help you out during the project? Do you have plans of raise funding for it? Or who, if somebody is looking you, who and what do you want from them? What AMPEX needs in order to increase, to be developed further, and to help out demonstrating this technology in the moon in the short future?
Well, and that's a very good question. As I said, we are in close collaboration of Moon Fiber team. It's a research group from Institute of Textile Technology and the Institute of Structural Mechanics and Lightweight Design of my university, the RWTH Aachen. They are already working with many organizations and big companies. So I will say that AMPEX will, as AMPEX team, not talking about the whole Moonfiber team, of course they must have different needs, but for us, for IGLUNA 2021, we will need for sure financial support because Switzerland is expensive, and we would like to bring the whole team for next year on Mount Pilatus and show our next iteration of the system working. And of course, if we are going to need more components and more working workload on the next iteration. So we will be for sure happy to work with any industrial company or any person that really believe on the AMPEX vision, and would like to be with us for next year, making possible a microgravity ready spinning unit.
Absolutely, and I think they will be very happy to to be in contact with you. Yeah, you set your linking web pages where they can find you, and I think we will put as well in the description of the video so they can reach you further. And I have the last question from the audience that is, I don't know if it is ready, but could you share if you have the actual fibers that you are using? Do you have a prototype or something that we can actually see how the fibers are in your project?
Yeah, for sure. Philip, you can take care of it.
I'm actually really glad that you asked this question, because I've just ran down from the spinning plant and disconnected the winding system. So you can here actually see the fibers that we just spun in the live demonstration. As we said, this is just e-glass. So basically the glass fibers that you use in internet cables and so on and so on. And we actually can produce a revolution speed that's high enough to get the same velocities as in the industry. So we can actually produce fibers that are 6 micrometers in diameter, which is basically the exact standard that the whole world uses. So you see, this is actually working, and we did it.
It's impressive, and actually it's very good to show in close detail that the system is actually working. It's not a proof of concept that is only visual. It's actually something that is working, and I think that will help you out a lot to continue with your project. I think this is all from our side. We are reaching out of time, so I would like to thank you, AMPEX, very much for showing us this awesome project. I will remind you that you can contact them in the description of this video. And also I have a survey there for everybody watching, in case you want to help out the Swiss space community and help the Swiss Space Center making this kind of events again. So thank you very much, everybody, for watching. And I will see you today at 1 p.m. with another project, this project 10. And then we will have Fabian from AstroCAD as a special guest to do a space talk with us. See you, everybody.